Boa tarde, good evening to everybody. It's a real pleasure to be back here for another seminar of the Observatory of Valongo. Today we have the great pleasure of having Professor Kanak Saha with us. And Kanak got his PhD in astrophysics from Indian Institute of Science in Bangalore in 2008. And then he has been a visiting PhD student in Baltimore at STSI from 2006 to 2007. He did several postdocs, among which a postdoctoral fellow at Asia in Taiwan, and then a Humboldt postdoctoral fellowship at NPE, and then a visiting postdoc at Geneva Observatory in Geneva. After that, he became an assistant professor at IUCAA, and now is an associate professor, and his area of research touches all aspects of galaxies. So I'm gonna leave you to him. I'm gonna share the screen. You can start the presentation, please. Perfect.
This is the full screen?
Yeah, it's full screen, and I'm gonna come out, and then can you hear me well now?
Yes. Can you?
Okay. Yes, perfect. It's perfect. Okay. So if anything happens, I will appear.
Sure. Thanks a lot.
Thank you, Kanak.
Good afternoon, everyone, and thanks a lot, Ariana, for inviting me to give this seminar. It's a real pleasure talking to you all. So without wasting time, I will start talking about the subject here. And today I'm mainly going to talk about our satellite, which is not new, is AstroSat, which was launched in 2015 October, and we have already celebrated 5th year. And I'm going to show some ongoing work that is we are doing with AstroSat, and in particular the Uv Telescope on board AstroSat. Here is on panoramic view of our institute. It's called Inter-University Center for Astronomy and Astrophysics. In short, it's IUCAA. Is founded 1988, not too long ago. Founded by Professor Nalikar. He's an eminent cosmologist. Many of you may know. And this is a kind of a leisure tea time activity in the premises of IUCAA. And IUCAA, we have quite a diverse research activities, starting from cosmologies, galaxies, relativity, X-ray astronomy, solar astronomy, and few other things are also like going instrumentation. And in IUCAA, we also is a very special institute in India, because it is one of the main institute which, or probably the only one, which has a very vibrant visiting program. So that is why it stands for Inter-University Center. We basically there are more than 500 universities in India, so people from universities can come and spend time at IUCAA, having doing their own research and talking to us, and there's like an activity here. Okay, so if you get a chance, do contact any of us, and if you come to India, visit us. So here is a broad planning of my talk. I'll try to motivate at every stage whenever it is appropriate. And I'll talk about the making of the AstroSat UV field and the two main results that come out so far. And is one with the searching the reionization sources, and an extended UV disk in distant dwarf galaxies and future outlook. So there are many reasons why one would want to study deep field, and there is nothing new to astronomers like you. So I will briefly touch upon why you want to study the UV deep field here. So one of the reason is obviously the luminosity function, the galaxy luminosity function, and this is the faint end part of the luminosity function, and the various observations are like done. So the faint end slope, the what is the slope and the faint end is basically the exponent alpha. This is quite an uncertain parameter, and in particularly you would also want to know what is that if you do the luminosity function in UV regime. Okay, that is one of the kind of my interest. And UV deep field, as you will see, is ideal, particularly the AstroSat UV deep field that we are making now, is ideal to probe ionizing sources from redshift 1 to 2. And redshift 1 to 2, as you know, probe a very unique era in the cosmic star formation history, when it sort of like had its peak star formation history, and since this is like sort of declining. And another aspect so is basically is that we want to be the one of the aspect of making the deep field is that you want to make a deep field which is having a high sensitivity and really deep in terms of a detection. So we will be able to explore the faint sources. Okay, that's the main one of the major outcome, I suppose, from the UV deep field, and that is what we will be targeting. And of course, this is all the famous Hubble deep field. So here's the part one with the making of the AstroSat UV deep field, AUDF. So here's a brief introduction of the AstroSat. Sorry.
What's going on? Let me take it out and put it in again.
I just lost my. Okay.
Okay.
Can you see? Thanks.
Yeah.
So here is a brief the outline of the AstroSat, the instrumentation configuration. It is mainly an X-ray. There are various X-ray payloads, like starting from the LAX PC, which is the large X-ray proportional counter, working from 3 to 100 keV, large field of view. Then the soft X-ray imaging telescope, which is working from 0.3 to 8 keV, and then this is the scanning X-ray telescope, and which is supposed to do the all sky monitoring in this energy range. And you have the cadmium zinc telluride, the CZTI, which is also a coded mask, X-ray the detector. And then you have the UV, the UVIT UV imaging telescope, working from 1300 angstrom to 3200 angstrom, and with a large field of view which is 28 arc-minute in diameter. It was launched 2015, 28 October, and this is the first space observatory launched by the Indian Space Research Organization, and in collaboration with the Canadian Space Agency and a few other collaborators with this external. And this is the very briefly the UVIT telescope. So there are two co-aligned telescopes, one in the FUV and in the NUV, and with a very small aperture, which is about 37.5 centimeter. And this was built in collaboration with multiple institutes in India, Indian Institute of Astrophysics, IUCAA, where we are, Tata Institute of Fundamental Research, TIFR, Canadian Space Agency, and all under the funding by the Indian Space Research Organization. So these two NUV and the FUV telescope can observe simultaneously. The wavelength range exactly like sort of kind of matches with the galaxy, as you all know. But we have multiple filters in the FUV. We have 5 filters in the FUV. These are the effective area versus wavelength curve. This is in NUV, and these are the different 5 filters. And where we have observed for the AstroSat UV deep field is this one, is the barium fluoride, with a mean wavelength around 1540 angstrom, and it's a white filter. So this is the one, okay, 154, the blue line. And NUV also there are 5 filters. This is dummy, and it's going all the way around from 2000 angstrom to around 3000 angstrom. And NEV silica, or the AN242W, is what we have used for observing the UV deep field. There are also like the VIS 5 VIS filters, but these are not used for any photometric measurements, but we only use for tracking purpose. So we use this for tracking so that we can correct for the drift and other stuff that are required for the satellite. And just to give you a one piece of like the image, this is an SDSS image, and you can see this is what I made it using the AstroSat, the far ultraviolet telescope. You can see and amazing details are available. So this was already a very promising for us to like now go to fainter this thing. So here is the first the planning. This is what the 2 big field of view, like around 28 minute diameter, and the intersection of these contains the good south field more or less. In fact, the large part of it, and each of them we proposed for 50 kiloseconds of observation in both these field. So we thought the simultaneously the overlapping area should have something like around 100 kiloseconds. This was observed right in 2016, and we have got the data 2017, and then there are many things happened after that. Like I mean, I started as a theorist and went to the observation. And when I got the data, the pipeline was not ready. So we did started work on the pipeline. So there is some altogether different story. But here is a brief UVIT observation, some salient facts if you like. So as I said, that the FUV and NUV observed simultaneously, and the delta T between the each frame taking is around 34 millisecond. It's a normal setting. But if you go to a partial field, you can have 600 frame per second. It's like quite fast. One can do. And in a typical good dump orbit, you have about 1500 seconds, and we have about 45,000 frames. And based on the experience, we see around 10% of these frames are affected by the cosmic rays. These are the cosmic ray shower, and these frames are totally removed by the pipeline. So we do not use this frame at all in the subsequent science ready images to make the science ready images. And this is how it looks like in one good dump orbit image. And you can see this is in FUV, and we mark some of the sources, which is like really you have to struggle to see because of the low number of photons. And then in the next dump orbit, the source may not appear at the same location. So we use the shift and rotation algorithm and stack them together. So we consider DCPU as a reference image. So we have around 40 such orbit images, and we stack them together and make the final images. And this is how it looks like if you go. So we recovered out of the 50 kiloseconds only 33 kiloseconds for this in one of the field, in another like around 34. So rest of the data are lost. So this is how we co-add them, and this is in far ultraviolet. I mean, I thought like, I mean, since 2016 to 2018, about 2 years I spent on the pipeline from a command line version, probably more than 10 pipelines, and going through each of these processes of coding by eye and by basically like there's no automatic program for this. Only the pipeline creates you only these images, this image. So rest of the time we have to do by post processing. And astrometry was also a bit of a hopeless. So I was trying to look for a redshift 1 good south sources. You can see, you can probably recognize. And when I try to put them, they're already outside the field of view. Somehow there was something wrong. So we did the astrometry by hand. So we use, this is where one of the the HST Chandra deep field south, in particular the extreme deep field part, and these are the HST images, and you can see when you do the AstroSat, which is how it looks like. This is the AstroSat image, and astrometry accuracy is around 0.3 arcsecond, which is about a sub-pixel in this. So in the zoom in part, this is how it looks like in far ultraviolet and near ultraviolet. And there is a comparison between on this side you have a AstroSat, the deep field part, and this is the Galax. You can see the clarity is much more because we have about a factor of 3 improvement in the PSF, and also the sensitivity is quite good. So you can go to a lot of paint sources in this. So we estimated the background in an iterative way. It's basically we took a patch of the sky or the entire field, and then we iteratively removed sources until we get a symmetric histogram for the sky background, and the mean is basically what we code for the sky. And this is in FUV, it is 28.4 magnitude per arcsecond square, and in NUV 27.6 magnitude per arcsecond square. And these are a work in progress, so we are still refining this detection limit. And with so far the 3 sigma detection limit in NUV is a 27.5, and FUV it is 27.9 magnitude. And this is the part of the AstroSat UV deep field. You can some zoom in part, and you all will recognize this the candles pointing the Muse extreme deep field, and this is what it looks like when you make a 4 pass band combined together, and this is what the extreme deep field looks like. So this image which we created using the PSF matching using 2 HST 814W and 606W, red and green, and cyan and dark blue are AstroSat, the 2 filters in NUV and in FUV. And they said the 3 sigma detection limit in far ultraviolet goes to 27.9 magnitude in AB, and in HST, if you go to the same the FUV filter, which is 150 LP, which is a 27.4, so which means that we can go about half a magnitude deeper than what HST could do in the same wavelength range. So there are various science goals now are currently under process. I'll talk about the XUV and the Lyman continuum detection. Okay, so here is the very brief introduction to that endeavor. The reionization, as you know, had sources from which the ionizing photons escape the sources, and one of the way to detect such sources are basically based on photometry. And so if you have a sort of filter response curve, which is for AstroSat, it could be 1300 and 1800 angstrom on the radar side. And if you have the photons whose wavelength is below 912 angstrom, and if it falls within lambda 2, then it is a credible Lyman continuum leakers. In AstroSat, the FUV filter, which is around 1800 angstrom, so if you divide by 912, the 1800, you get 1.97, and if you subtract 1, so you get any sources which is at a redshift greater than 0.97, and if it is detected in FUV, will be considered as a potential Lyman continuum recurse. And for a redshift 1.4, this is the Lyman limit, 1 plus z times the 912. So which is at 1.4 redshift, we have 2207 angstrom, so which is much greater than this thing. So within the FUV filter of the AstroSat. So why we want to know? So of course, like the many of you have seen this probably more than 100 times maybe. So our universe went through a phase of phase transitions. Once this is the recombination, which is around 400,000 years old, when the universe, the recombination was complete, and the universe went through a dark phase. This is called the cosmic dark age. And there were only like the from the recombination, you have mostly the hydrogen atoms and probably and other Big Bang nucleosynthesis products like some amount of lithium and helium. Now this dark age lasted for about a few 100,000 years old, so around 0.1 billion years when the reionization started. How it started is it started with when the first stars and the galaxies formed. And when the first stars and the galaxies formed, they were probably very massive and also very hot, so they would emit in extreme UV. And since they would be short-lived, also the photons would escape, must have escaped those objects. And those photons started, which are the ionizing photons, they started like ionizing the rest of the hydrogen atoms, and that's how the reionization universe went through a phase of reionization again, because it was ionized in the beginning and is going to reionization phase again. And it went up to around redshift 6. So there are a lot of uncertainty here when exactly the reionization ended and when it's exactly started. It's like it's still an ongoing debate, and we are yet to find what the exact epochs are. However, when the reionization sort of completed after around redshift 6, then the photons could pass through and we could observe again. And that's how like we observe. Now the question is, what are the kind of sources that reionize the universe? That is what we want to know, and that is what we are looking forward to. Now the ionizing photons can't escape the galaxy easily. There are currently two different kind of models. So imagine this is like the Stormgren sphere, which is like ionization bounded nebula, where there could be like if a very strong starburst, there could be holes in the Stormgren sphere, and through which the ionizing photons could escape. Otherwise, normally the ionizing photons would be absorbed by the hydrogen atom in the interstellar medium. Or it could be the starburst could be like so strong that the Stormgren sphere only form partially, and then the Lyman continuum photons or the ionizing photons would escape with the starlight. But we do not know yet which of these pictures are the correct pictures. Correct picture, and we are yet to find. Maybe there is a mix of both. We don't know this, but it is a difficult process. But then it is not only the ISM which can absorb these ionizing photons. The galaxy might also have the circumgalactic medium. So the some of the photons which may escape can also be absorbed by the circumgalactic medium. Not only that, so even when they escape the ISM and the CGM, they have to travel all the way from the source to U, which is the path is filled with the intergalactic medium. The photons could also be absorbed by the intergalactic medium, the clouds. And then finally at the end, the photons that reaches U is like very few, and that is why so far very little detection known about the Lyman continuum recurse. there is like this IGM part is like very well studied, and this is where the transmission curve, or in terms of like optical depth if you like, and this is where the mean transmission, as you can see, as you go to the higher and higher redshift, transmission drops like very sharply. So that is why it is very challenging to observe the ionizing sources from redshift 6 and 5 or 6 like that. And that is where the key, that is what we want to. However, if you go to like lower and lower redshift, the IGM transmission is pretty high, so there is a good chance that we can observe. But even then, there has been like very few detection. And this is summarizes, this plot summarizes the so far the known detections. I may have missed some of the recent ones. And in 2016, Izotov et al. Had published a series of papers, which the green P galaxies, the young low mass starburst objects, which were using the HST cause. It was found that they are Lyman continuum leakers. And then 2018, when I was almost ready with the deep field, there were one paper from Seidel et al. Using cake and around redshift 3. But still it gives you from redshift all the way around 0.4-ish to all the way around 2.2 or 2.5. The entire area, there were no detection of this. And you can also see these are all color coded, and most of the colors points to around the 900 angstrom, which means the photons that you the recorded in the detector that you observe, that are around 900 angstrom. And we'll see. So we had the first detection of a Lyman continuum leaker from AstroSat at redshift 1.42, and as you can see, this is the Lyman limit, and FUV filter is completely within the Lyman limit, and this is the so we had the first detection which appeared in Nature Astronomy last year. And how we have detected this galaxy, we have actually gone through about 1517 galaxies with spectroscopic redshift, and then of which we have selected a sample for which there is simultaneously H alpha, H beta, and O3 are there, and this already downsized the sample and 942, and this is like a redshift range from 1.1 to 1.55, of which there were 38 galaxies in the Hubble extreme deep fields. This is where we concentrated first for our search, and only clean signal to noise greater than 3 in far ultraviolet sources are chosen, and only 2 qualified, of which we chose one which had one of the highest H alpha and O3 equivalent to it, like that's quite high, and these are observed equivalent to it. This is how the source looks like. So the source in AstroSat, this is the image, and this is detected with a signal to noise around 3.2, not 4 or 5, but it's 3.2. And this is how the source, this is simultaneous detection in NUV, and this is in FUV. In FUV, this is the 28.5 magnitude, and in NUV it is 25.6 magnitude. It's quite faint. This is how the galaxy looks like in HST 3-color image. As you can see, the galaxy has 3 big clumps and the fourth clump is a C4. And we had this task that whether these clumps belong to the galaxy or they are like foreground. In particular, the doubt came from the C4. So we looked at first the photo G estimation of these clumps, individual clumps. So using HST. So these are the ACD, and then we used the easy and the fast to determine the photometric redshift, in which the second clump C2 had a kind of mismatch in the redshifts. I still could not figure out why. And we measured the clump mass, in which we subtract the galaxy as a background. And the clump mass to galaxy mass ratio around 0.47, which seems to be normal for clumpy galaxies in the good south. But we had HST GRISM. This is the GRISM G141 data from 3D HST survey, and you can see clearly there is a O3 and H alpha line detected, and this is the GRISM 2D image of that. And we actually what we did is basically we did the emission line mapping from the GRISM to the direct the light image in F160, and then we map to the clump level at then, and then using that we the C1 and C2 are more or less co-aligned. So we have C1 C2 are at redshift 1.4, and C3 is also at redshift 1.4, where for C3 we had to mask all of this and only get those pixels which are within from the GRISM, and this is how it is the detection, the mask. And although the signal to noise is not 3, but there seems to be like sort of clear peak here, the detection. So we had sort of shown that all the 4 clumps are at the same redshift. Okay, and interestingly, this is the first clumpy galaxy with a Lyman continuum leakage in the high redshift, and in particularly, as I said, that this redshift range, which is around between 1 to 2, and many such, as you know, many galaxies are clumpy in this redshift range. So this raises like hope to look for more such clumpy galaxy, as opposed to people who were already thinking that the only Lyman continuum leakers could be the green piece, the compact local starburst galaxies. But we have now examples of the high redshift clumpy galaxies. We did the ACD modeling using SIGAL, and we had the stellar mass determination from the ACD, which is 1.4 into 10 to the power 9 solar mass. We have the indicated star formation rate, about 55 solar mass, and with the mean metallicity 7.004. And this is basically the oxygen, based on the oxygen abundance. We also have the determination of these things from the spectra. As you can see, the SIGAL modeling below 1000, this is the Lyman break, and this is at a rest frame of 600 angstrom, around 600 angstrom, and no SIGAL modeling did explain this this flux from the AstroSat. So we did a BPAS modeling, and we found that if we and see the BPAS modeling and cloudy simulation together, and in which we found that if we put in these other parameters, and from the spectra, if we put this as an input, we need to have a very little dust in that, like color excess of 0.01, and the low column density of the hydrogen, and only then this sort of the matches with that. But then we have an issue that it overestimates the model is like doesn't match on the beyond the non-ionizing part of the spectrum. So this is an issue right now. So we do not we still, this problem is open. And I think more of this modeling, we have a similar issue, the ACD modeling part. So we calculated the escape fraction in various ways, like we use mainly 2, which I will show you. So we use case B recombinations, so standard stuff, like the textbook stuff. We first calculate the number of photons that could not escape, which is the non-escaping photons, using the H alpha luminosity from the GRISM. And then using AstroSat FEV filter, we have the luminosity, so we calculate the photons that were detected. So we know the number of photons that escape the galaxy. And then we use the IgM opacity, which is the median value is 0.29, and we get with a transparent IgM, we get at least the 0.2, which is 20% of the ionizing photons escape the galaxy. Or if the mean tau is 0.29, you get around 0.25. We also use the standard practice in which one uses this is the ratio of the ionizing photons to the non-ionizing photons, the 1500, the observed and the internal, means the intrinsic modeling that came from the BPAS modeling. And typically one uses 900 angstrom, so but the rest frame, the observation is around 600 angstrom, so we use the 600 to 1500 ratio. And then you get the IGM attenuation, internal extinction. So that's how you calculate the absolute escape fraction. Okay, and these are the sort of the distribution of the escape fraction. And you can see that the at least our conclusion is that 20% of the Lyman continuum photons escape from this galaxy called AUDF-01, the first one in that. And this kind of a nice numbers that is expected for the such galaxies if they were to be in redshift 6 or above. So now we have this revised picture, and you can see this is the one detection, the first detection. We hope to populate this soon. And you can see that there's a striking difference between all other detection, because this is at rest frame 600 angstrom. So which means that this galaxy is emitting 600 angstrom photons. And certainly, like, this would be useful to constrain the below the Lyman break, the ionizing spectrum of objects. And it's probably, it will be good if we have more such things to see how to constrain this part. So this is the AstroSat FUV deep fields. We have many such detection already, and we are currently working on that. And this is kind of the improvement. We have several observations now, and currently the data analysis is going on. And this part we can see that will be probably the AstroSat ultra deep field now in future. I quickly go to the last topic of this, and in which I talk about the extended UV emission. And to me, this is one of the major discovery of galaxies, the extended UV emission that is found in local spiral galaxies, galaxies, and this kind of gives you an signature of the cold gas accretion or the inside-out growth of galaxies. Sorry. So we looked at 14 blue compact dwarf galaxies from good south, and these were based on some such criteria, which I'm not going into detail, but these are, like you can see, if you take the good south, these were the only 14 BCDs that shown. This is my student Anshuman, is his PhD thesis, is working on that. And we wanted to basically ask a similar question, whether the BCDs also grow inside out, and they show this extended UV emission. This is the picture in brief. This is the AstroSat image, and this is the HST 435W. This is the B band. And you can see the green ellipse is the optical boundary or optical radii of the galaxy, which is the PSF convolve, which means that the UVIT PSF is around FWHM around 1.4 arcsecond. So we sort of convolve the HST image with that PSF, and this is the blurred sort of PSF convolved optical boundary. And this is the far XUV or the FUV boundary, or the FUV radius. And then the way it is done is that this boundary has within which we have signal to noise greater than 3. So that's how we construct this boundary. And one of the BCD shows clearly the clumps for which there is no optical counterpart, and these are basically the type 1, the XUV disk of the local counterpart in spiral galaxies, if you like. And typical masses that we found around 10 to the 6 solar mass. So we have now several examples of these galaxies. Of 14, I think we are around 5 of them show these clumpy FUV clumps for which there is no optical counterparts in and around. So we did a detailed surface brightness modeling. So we calculated the this is the NUV and FUV, the intrinsic surface brightness modeling, based on the 2D, but we were showing the 1D profile. And so we estimate the size, the optical scale length, and the FUV scale length, the intrinsic one. And this is how actually the UV80 PSF looks like. You have a core, which is a Moffat, and you have an extended wing, which is used here because we are looking at the extended UV emission in these galaxies. So there's a large wing in that. And so this is how we calculated the light, total amount of the XUV light within the annuli between the optical and the XUV boundary. And this is how we show them. And this is the ratio of the FUV to optical scale length. And we define in our working definition that those galaxies for which the scale length, FUV scale length, is larger than the optical scale length, intrinsic one, and for which delta Lx, which is the amount of the XUV or FUV light, which is like more than like sort of 0. So this is this goes well with the definition of the Tilker et al. Definition from the local universe. And as he said, that these galaxies are all at redshift around 0.1 to 0.3. So we also calculated the clump in following time scale using dynamical friction. And we got a time scale about 6 giga-year, which is not too short, not too large. Sort of, we think that maybe several such FUV clumps fell into the central region and may be responsible for the BCD phase. And also, like, there are several other interesting results also, like, came with this, because you can see here we also go to a very low density the star formation rate, because these are really probing around 10 to the power minus 5. So that's also an interesting result from this. And with this, I would come to a conclusion. There are several people who have contributed to both this work, and then there's ongoing work, and then this our collaboration is sort of on an increasing. So I welcome interested people to contact me if you are interested. So thank you for your attention.
Thank you very much, Kanak. So
should I stop sharing now?
Yes, and I will try. Okay, I'm appearing again. So yes. Can you see me?
Yes.
Okay. So thank you very much for the very interesting talk, for the great work you have done in the reduction process and everything. So I have a first question from Thiago Signorini Gonçalves. That's a professor here. Well, that is a professor at Valongo. So I'm gonna make it appear. So great talk, thanks. About the Z1.4 galaxy, sorry if I miss, what is the stellar mass? We expect...
So yeah, the stellar mass is from the ACD is 1.4 into 10 to the power 9 solar mass. We expect at Z frequency that low mass galaxies, and exactly because probably even lower mass. So but low mass galaxies are now the prime suspect for them to be responsible for the reionization at redshift 6 and above. So yeah.
Okay. Thank you very much. So I have a maybe naive question, which is how many sources do you expect to find to populate the plot where you show that there are objects already in the literature at lower redshift and at higher redshift, and
I think I missed you. I'm unable to hear you.
I'm here. I'm sorry. I think my connection got lost. Can you? I'm sorry.
Yeah. So yeah,
Okay.
I got the point. You said that you asked how many such objects
You expect to find.
Yeah. So so I don't have a very concrete answer to that, but it's based on the experience so far which I've done for searching. So as you can see, um, of around 40 we got one. Like, for example, the main problem is that we need to have the spectroscopic redshift done. And then within the UVIT PSF there should not be another source. So even if some sources are looks like that it is a Lyman continuum recurse, but maybe there is some other faint source within the PSF FWHM, and whose redshift we do not know, then we discard that sources.
Okay.
So that if you have a big spectroscopic detailed survey on the good south, it would be like amazing. Like, for example, Muse is doing like sort of IFU. We have now know lots of like no objects right now. So I think it's like maybe 2 in 100 such.
I see.
Yeah, it's not very it's not a lot, but it should be surprising otherwise.
And which precision would you need in the redshift? Like, if not spectroscopic, let's say it's a multi-band photometric redshift. Like, do you have an idea of the precision you will need?
Yeah, so the main point in this, while I face the publication and talking to in one few of the conferences, that the some objects, for example, there was an object called the Ion 2, which is I think redshift around 2-ish or above. I think no, maybe 3. I forgot the exact redshift, but it went through a bit of a turmoil. I mean, at some point, people thought that this is a Lyman continuum recurse, but then they found another foreground source, so it's out, and then probably it came back again. So I think people probably, I don't know, maybe don't believe without unless it is spectroscopic redshifts.
Okay.
So I think even if it is a low resolution, like we have used GRISM, for example. GRISM is only like 100, so the lowest resolution, but it's a very good like this is an HST. So, but I think they believe more probably spectroscopic redshift. But I will not comment on this because we are mostly doing spectroscopic redshift as a search criteria for that.
Okay. Yeah. Then we have a question from Denise Rocha Gonsalves, that's a professor at the Observatory of Valongo as well. And she's saying, thanks for your talk, beautiful results. Sorry, but I don't know if AstroSat is open for all astronomers. So can you comment on the policies to get use data of AstroSat?
Yeah. So AstroSat is the first year it was not open. It was in which is in 2016, going for the like guaranteed time. After that, it opened as 10%, 20%, and now it is fully open. And anyone can observe. We send proposal, and there is also the data which gone outside the proprietary period. Of course, those data are like raw data, not totally science ready images, but there are also science ready images are available on the ISRO site.
Okay. In
so
the
you can
ISRO.
actually browse through and then download if you like.
Okay.
It is available, and also it is available for outside astronomers.
Okay.
Fully.
So we have a question from Karin Menendez del Mestre, that's a professor at Valongo. You showed the difficulties found to make the ER portion of the SCD match to the optical light. What possibilities can we consider aside from a non-universal EMF to reproduce the observed spectra?
Yeah, that's a good question. So the first of all, like I only tried with the Seagull modeling. In the Seagull modeling, we looked for all the two IMF, which is the saltpeter and Xavier, and so this part has not been explored apart from that, and we did not find much between the saltpeter and Xavier when it comes to the matching the ionizing part of the ACD, which is like below the Lyman break. With the but then that's how, as I said, like we did the BPass, but if you leave that AstroSat observation, then rest of the spectra are, I think, well modeled with the saltpeter IMF. So I don't know if did I answer.
I think so. I don't know. So Karin will answer. So Denise is thanking you for your answer. And I got curious also about when you were showing galaxies, nearby galaxies, and the blue compact wars. But I was thinking about the possibility of using Uv minus NUV to study even nearby galaxies. I don't know if somebody is looking at this with AstroSat, like looking at the bulges of nearby galaxies.
Yes, I think from the deep field, I'm completely below redshift of 0.97. I have not looked at any of them. I think there's excellent data is also available right from using the deep field. There's nobody looking at that.
Okay.
If you're interested, I am very happy because there is a good amount. I mean, there is definitely, you saw in the BCDs, it's quite good result came out of that. And yeah, frankly speaking, nobody is looking at the bright galaxies for which is like very good signal to noise data available, both in FUV and in NUV.
Okay.
And in the southern hemisphere. So it's in your part.
in other side of the sky.
Yes.
Okay, so Karin says that yes, you have been, that is tricky, but that she's thanking you.
Yes, welcome, thank you.
Okay, so, well, I don't know if there is any further question, but in the meantime, I would like to thank you a lot, also because I know there is quite late in the night. So thanking you a lot for giving us this talk. And I hope, maybe you'll come to Brazil one day or we come to India, because we are all part of BRICS. So
yeah, that will be very good. So you guys can plan, and then we can do something, even seminar or meeting. That would be great. I look forward to.
So Karin is asking another question, which is, I'm sure I miss it, but what is the special resolution of AstroSat?
So is the PSF, the FWHM is 1.5 to 1.6 arc second in far ultraviolet, and in NUV it can be as good as around 1 arc second. Okay, and the pixel resolution is a 0.4 arc second. Like that's the subpixel.
Thank you very much. There is another question that I have missed. I'm sorry.
Okay.
So is Douglas Brambilla, who is a co-organizer of the seminars and is a student in Valongo, saying thank you for the talk. Can you talk a little bit more about why you say the extended UV emission is one of the most important astronomy discoveries?
Okay, the way this is like sort of, I know it from the XUV emission, UV emission from the spiral galaxies. So there are two aspects in this thing. Is that one is FUV. If you observe the extended UV emission FUV, so FUV, as you know, um, it probes the light emitted by objects which is of the 100 to 150 mega year old, which is basically saying that we are probing the very recent star formation region, like of that time scale. So if you see, that is the outside the optical, where there is, you apparently with the current resolution you don't see stars but you see extended UV emission, then it means that there is a if you believe that there is the FUV emission is not due to some other reason but it's like star formation, then it gives you an idea that is a star forming in the outer part of the galaxies, and where we do not have the optical counterpart, and that's why of course is extended. So which means that, and then the stars cannot form on its own, it needs like gas. So which means that this is in some way saying that um, there's a star formation activity going on, and it has to be if it has to be in the outside, then it has to be from the gas, and where do the gas come from? So it has to be an accreted gas. Okay, otherwise there is no way you can keep on having this extended UV emission. This is what way I think. So it gives you an idea about the accretion, gas accretion in that sense. Of course, one needs to be very careful to actually, because the as you know that we do not have a direct probe of that. We observe gas accretion from the filament, maybe only few examples are there, if I remember, on which you need to do the spectroscopy properly to understand that the gas is falling or accreted with the galaxy. So this gives you an indirect way of like going towards that, and also it gives you like if the galaxies are growing inside out. So which means like this extended star formation, which will be adding to your the host galaxy in some sense, if you like. So this gives you basically an idea, like one of the picture in which we see it in observation that that the galaxies are growing inside out, and 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 that is one way. And the other thing is that, to me, another interesting part is that how low the gas surface density to like sustain star formation, like the basic the question of probing the low density star formation rate in some sense, which I think is a good way to probe this. So if we have now the gas in where you see the XUV or the molecular gas, it will be an excellent thing to close the picture in that sense, and you will know like the how low star formation rate, how what is the low density star formation rate, how it happens, what is the physics of it basically. So that is why I feel like this is a good, I do not know is the most important, but it's an important, but from galaxy I feel this is one of the most important discoveries.
So Douglas says thanks. And then Karin adds that there are a nice possibility for a myriad of galaxy studies. Thank you, and she thanks again for your talk.
Okay, thank you very much.
So okay, we did 1 hour, and so I think it's good. And well, yeah, thank you again, Kanak, for this talk.
Okay. Bye everyone, and thank you. Thank you for having me.
Ciao. I'll stay here. No, you can stay. Let's just close here.
Okay.
So yes, see you soon in the seminars of Valongo.
Okay.